Okay, hello. In this video, we're going to look at the planets program. I think we'll still make some more changes, but this is what it is right now. So let me go ahead and run the program. So this is the way it looks right now. You have S for the sun, and each of these letters stands for one of the planets. It roughly corresponds to the scale of our solar system, and this is all sort of doing calculations using each object has a mass, and based on that mass and the distance from the sun, there's some pull of gravity, and each object has some velocity. So let's at any given point, the E here, there's some sort of pull of gravity towards the sun, and it has some velocity going in the direction it's going, and those things together, there's equations basically to tell it where it will go next. It's getting pulled a little bit this way towards the sun, and it's going this way, so that sort of pulls it into a curved path there. All right, let's take a look at what the main pieces are to the code, and the plan will be to make some changes to this. Okay, so the files we have, there's a make file, there's a header file, objects.h, where our classes are defined, where most of the code is, and objects.cpp is the code, so we have the definitions of the classes here, the definitions of the functions in here, and the main program is in planets.cpp. Let's look at the make file first. Pretty normal make file using G++. We have the debugger stuff turned on, lots of warnings, so we're supposed to do things the right way. And then we have the objects.cpp, the planets.cpp, and this is a curses program, so we have the link and curses in there as well. Going up to smallest to largest file, go and look in the planets. It has the main program, and if you see here, it is very short. I don't need that anymore. So everything really is inside of the classes. If you look up here, things that we're going to use potentially, definitely vector to keep track of the different objects. Some timing stuff coming out of this file. Potentially using printf for debugging, and curses for doing the updating on the screen, and the math stuff for doing some of the equations. Where we come into main right here, right now it's not using command line arguments or anything, it just starts. So there's some object of type world t that's going to be defined in this header file, and basically that object is going to have functions for the most important stuff to happen. So here this initializes the curses stuff so that we can draw on the screen. This one here is going to load in Sun, Earth, Mercury, etc. With the values, for mass and distance and stuff from our solar system. And then we have a loop that goes forever. So inside the loop, there's a function to compute the strength of gravity at that instant for all the objects. Update the velocities, because so if you have, just look at the cursor here, if you look at that moving, if there's gravity pulling it this way, that changes the velocity. So that gravity changes the velocity. So we update the velocity in this update function, and also the position. So first you update the velocity, and then the velocity pushes you in some direction. So these two happen repeatedly forever. And then every once in a while, we draw an update to the screen. Inside of the W, there's a redraw rate that says how often the screen should be redrawn. Right now, it's set to 1 second. We can change that and see what happens. So this is supposed to say that if the time since the last redraw is larger than the redraw rate, larger than the redraw time, then go ahead and this function here will draw the screen again and save the function clock there. The function clock there returns something that's of this type, clock underscore t, which is going to be some sort of integer that counts how many clock ticks since the computer rebooted or something like that. Okay, so how many clock ticks, and then there's a clock ticks per second. So if we look at the number of clock ticks since the last time we redrew the screen, divide by the clock ticks per second, that tells us how many seconds since the last time we redrew the screen. And if we want to see what effect that redraw rate has, it's initialized in this file somewhere. So right now it's set to 1. If we update that, let's see. What did we change? That is not used, so get rid of that. All right. So now this is updating every 1/10 of a second. It looks a lot smoother. Still choppy because we're in text mode here. And then I'm Control C to kill. Okay, so that's the main function. Then everything happens inside of this world T object. So if you want, you might want to just kind of pause to get the overall structure of things. And then if the while loop ever ends, which it doesn't currently, but we could put that functionality in, we would clean up the curses stuff, and the curses part of the program. Alright, so the next thing that we want to look at is the objects.h. Let's start with the world. A lot of these functions we've already seen. So get screen ready for curses drawing. Stop curses stuff. So those we already saw. This compute G, recompute strength of gravity for all objects. This uses gravity for each object to update velocity, and then also position. This redraws the screen. Load solar system, right, I'll just leave that the way it is. These other ones we haven't seen yet, so we'll get to those. The variables that we have here, this stuff is, these are the planets, etc. in our solar system. Each one of those is an object underscore T, and we have a vector of those. So if we go back and look at the object underscore T, each one of them has a mass, which is a double, has a position, a velocity, an acceleration, which is a point underscore T, and a character to display. And I'm using doubles instead of floats because precision will matter here. It may actually make a difference whether we use doubles or floats here in terms of the accuracy of the simulation. Each of this position, velocity, and acceleration we're doing in 2 dimensions. So if we look at our simulation here, the Sun, the Earth, Mars, Mercury, they all have a position in terms of x and y, so I'm thinking of the Sun as kind of near 0, 0, and then to the right would be x goes bigger, to the left x goes smaller, up y goes bigger, down y goes smaller. Okay, so the position, each one of them should have an x and a y for the position, and also the velocity is you have a, are you going left to right? That's your x velocity. Are you going up and down? That's your y velocity. Same thing for acceleration. Are you speeding up in this direction? Are you speeding up in this direction? Okay, so that is the way to think about position, velocity, and acceleration. It's a cute thing that your position is x and y, and also your velocity is really x and y as well. You have some amount you're going this way, some amount you're going this way. All together, that gives some kind of direction. All right, so each one of those objects has a mass and those 3 things, and a character to display. And that is the main information that we're keeping. This here is for cursive drawing. That'll be used there. The redraw rate, we've already said what that means. And these other ones I think we'll get to as we look inside the different functions. Okay, so question for you. What is the name of this world_t method? Okay, that is called the constructor. So what happens in the planets.cpp in C++, when you have an object, a variable it's a C++ class, some initialization will happen for this automatically, and with the way we have it right now, it would run this constructor. So we have to go and look for the code for this constructor. The semicolon there means this is just the definition of it, the prototype of it. We have to go and look for the code in the objects.cpp. So I'm looking for world_t with parenthesis. Okay, so this is it here, and this is the way you have to do the definitions of class methods outside of the header file. So let me go over here, back to the object. So in here we have class, it's a keyword, then you have the name of the class, you have a curly brace, we've been doing public, we'll leave that there. We have names of variables, names of methods. Now I don't have the definitions of these, there's just a semicolon. And then we have a curly brace to close the definition of the class and a semicolon. Alright, so at this point, just by having that information, the planets.cpp, so planets.cpp, just by looking at the header file, knows what methods are available inside of this variable. It doesn't know what the code is, but it knows which ones there are. Alright, which is all the C++ needs when it reads this file. It doesn't have to know what the actual definition of this is, it just has to know that it exists to tell you if you have an error in your program. Alright, so that's the way we split this out. The header file has just the layout, the outline, and then we go over into the CPP file to give the actual code. And over in the CPP file, we don't have class world_t again. Instead, that's already been defined, and the objects file, the CPP file. We know that that's already there because we pound include the header file. And then the syntax here is, this is the name of the class, so that matches up with what's after the class keyword there. So that's at the name of the class, and then double colons, and the actual function name. So if we want to look for one of the other ones, there's init curses. We have void, that's the return type, and then this is the init curses method inside of the world T class. All right, so now this is going to run right here. So right when this variable is declared, this constructor happens. We just do some initialization. So we're going to have the redraw rate every 10th of a second. This time step is going to be every little calculation that we do in the update. So when we were up here, when we do the update, we're going to use the velocity. Let's say my cursor here is an object that's moving. I could calculate what is the velocity for this, and then based on the velocity, which direction it's going, I would move it a little bit. Okay, and this time step over here is how much time are we going to let go by each time we move the objects. So depending on how fast it's going and how much time we have go by. And this is just some formula. Is something like. So this is something somewhere around the ballpark of, so that if we let our program run, it'll take about 20 seconds or 40 seconds or somewhere kind of in that range for one orbit of Earth. This is the number of seconds in an Earth year. I want that to take 20 seconds, and my clock is this many clocks per tick, so just sort of something. All right, these are not, so those are just dummy values that are not used at the moment. Okay, so we've gotten to the end of this. We just initialized a few things. Now we go into the init curses function, and this is code here that will basically be at the beginning of any curses program. And ours is hiding inside of this init curses function. Okay, so we initialize a screen that we can draw on. We're not displaying characters that are typed. If we are going to take user input, we don't have to wait for enter. Right now I'm not taking user input. And this is also about taking user input, which we're not using. And then there's a dummy check to make sure that the screen was actually created correctly. Okay, so that just gets things set up so that we can do curses. All right, now load the solar system. Let's go to load the solar system. Okay, so in the load of the solar system, we have basically a bunch of add object. We go back to the header file. There was a function called add object inside of the world. So this is going to create a new object and put it in the stuff vector. We have the stuff vector up here. Okay, so add object. Here we have x coordinate, y coordinate. So where is the object going to be? What is its display character? And what is its mass? So here we have, I'm thinking of the sun at 0, 0. That's the middle of the coordinates, and then a mass of this. And I just looked that up, and I'm using kilograms here. So there's a website. must have gotten that from somewhere else. This is all the planets. Okay, so but that's the mass of the sun. This one here is Mercury. So if we look up Mercury over here, here's Mercury. It has 0.330 times 10 to the 24th kilograms. So 0.330 times 10 to the 24th. And the distance, the average, this is some kind of an average distance, 57.9 million kilometers. So 57.9 times 10 to the 6th. And then I have, right now I have running Sun, Mercury, Venus, Earth, Mars. This G is something that gets used in equations. If you want to look it up, you can search for, I guess I'll say C, Newton's law of gravitation, and you'll see something about that. It's not critical. It is critical that the units that I use match up with other things. So here I'm using units of kilometers and kilograms. So this is kilometers, this is kilograms, and this constant here is given in terms of kilometers, kilograms, and seconds. Okay. So the sun's at the middle there. I put Mercury here, so I can ask you a question. If this is the x-coordinate for Mercury and this is the y-coordinate, where is that going to put that relative to the sun? So pause and answer that. Same thing for Venus, Earth, and Mars. Okay, for Mercury, this is the x-coordinate, because that's the first thing here. This is the y-coordinate, so x goes left and right, and positive goes to the right. 0 means y-coordinate of 0. So let me go back to my screen that had stuff. If the sun is here, positive for x goes this way, and 0 for y would keep it right here. So when the thing starts, Mercury should be over here. All right, how about Venus? So Venus, I have nothing for x and positive for y. That would be up here when it starts. Earth, I have negative for x and nothing for y. So that would be over here, negative. Sorry, that was negative for x. Right, negative for x and nothing for y. And then Mars, nothing for x, negative. This was negative for x, nothing for y. And then we have nothing for x, negative for y. That would be down here. So I just have them sort of going like this, so they're not all bunched up on one side. All right, that's those. There's the gravity constant that never changes in the rest of the program. And then there's two things that happen that you're not going to have to probably change. So this right now creates objects. Let's go ahead and look at the add object function. So here's add object. What do? We take those parameters, the position, the character to use, and the mass. We have an object, and we push that object onto the stuff vector. So question for you. This object that we just created, that's going to go into the position, the character, and the mass. All right, and where does that happen? That happens here. So we'll just pause. Okay, we'll stay on this for just one more second. So we're in the add object. How did we get here? We were in the load solar system. All of these add objects happen. So add object is a method inside of our class. We go to that method, wherever that was, add object. Here it is. So the first thing that happens there is we declare a variable that's an object t. And what does this mean right here, this business? Okay, so we're declaring a variable that's an object, and we have parentheses after it. Normally, parenthesis means function, right? calling a function. And that's actually what's happening here, that we declare a variable, and when we declare a class variable, a function runs. What is the name of the function that runs when you create an object? Okay, that's called a constructor, and that should be in the definition of the class. I have the object t here. There's data inside of it, and then there's this function which has the same name as the name of the class, and here it has parameters. So the constructor that we had for world t doesn't have anything in there. The constructor we have for object t does. So this was the object t class, and then over here in the add object, what happens is it's going to call this function with these parameters, and the definition of the function is not right here. I have this semicolon. I don't have the definition of the function. I have to go up in this file. It happens to be up here above, right here. So object t is the name of the class. Object t is the name of the function. The constructor doesn't have a return type. There's no return type here. That's just a rule. And then this basically just saves the values. So we have the mass is saved from the parameter that goes into the mass member variable inside of the object. X and Y go into the position, and the character goes into the display. So this thing here sets up the mass, the position, and the display. All right, question for you. After that happens, what is going to be inside of the velocity and the acceleration? This function doesn't do anything with velocity and acceleration, so what is going to be in there? There are two things that you might think. One is, how about zeros? Maybe. Another is, are there some default values for those inside of the point t? So let's go and look up at the point t, right? Because these are variables inside of the object. They are of type point t. So when this object is created, which this constructor runs when the object is created, these variables are also created. So what happens is, there's a constructor for the point t. We have to go and look that up over here. Here's the point t constructor, and what it does is just set zeros to x and y. What that means is anytime we declare a point t, if we don't put anything in there, it will be zeros for x and y. All right. So we were inside of the load solar system. Let's see, go back. Load solar system. We added the objects. We gave positions. What is in the velocity for each of these? In the add object, there wasn't a velocity, so that's just going to be the default values coming from the point constructor, which is 0. So if I put those objects in, they would be at certain positions. They would have 0 velocity. What would happen if you turned on physics? The Earth, so the sun's sitting there, the Earth is sitting here, doesn't have any initial velocity. What happens? If this was real life, then if there was no velocity, gravity pulls the Earth towards the sun, and it just falls down. And I can actually simulate that. This set initial v is going to put velocities in. So if I take that out, there'll be 0 velocities, and we can see what happens, probably. So things just fall, and they might, so they actually will fall, and then when it gets on the other side here, it gets pulled the other way. So, yeah, all right. All right, so the set initial V is supposed to put in initial velocities so that things basically go in circles, ellipses. All right, and the way that happens is with some equations. Here is the Venus. It's a certain distance from the sun. Gravity's pulling it a certain amount this way. There's an equation for that. And there's another equation for if I have a certain velocity going this way, what happens. I don't really want to explain the equations. Just go to the set initial V. There's two things that happen. Calculate center of mass of the whole system. So that's supposed to take into account all the objects, and really the sun is the only one that's really going to matter for us for this solar system, but we could have, you know, more than one sun or something. So it just takes a combination of all the different objects and multiplies and adds together masses to give some point that's basically the center. All right, and I store that inside of, there's a couple variables here that we hadn't looked at yet before. The center. So the center of mass is going to be the position that if you average all the masses together, that's where the average is. And mass is going to be the total mass of all the objects. And that comes out of the center of mass function, which we just start with a 0, loop through all of the objects, add on the mass. So this just computes the mass like that. And the center position, we start with it being 0, 0. And then after we know the total mass, we add the position of each thing in the objects, but weighted by its mass. So things with a higher mass, their x value matters more. This is just a weighted sum. It's not, yeah, it's just a weighted sum. We're not going to have to mess with that either, so you can just forget about it. All right, then we are inside of the initial velocity. We calculate the center of mass. Some error debug printing that we don't need right now. So then we're going to iterate through all of the objects. This actually starts with skipping the first one. I don't change that to see what happens if we put a 0 there. So for each of the objects, this is the acceleration due to gravity towards the center. It's equations. You don't have to worry about it. If you don't want to, you can just leave it there. So this is supposed to be the force of gravity for the whole system on this object. We have the center of mass and the total mass. So this is the amount. This is the amount that Venus is being pulled towards the center of mass of the solar system. So that's one thing. And then the other thing is if you have an object, then what is the centripetal acceleration? So that is if something is going in a circle, what is the force on it to keep it in that circle? So if I want to keep something in a circle, then the force that I need to keep it in the circle really is the same as the gravity. So then I set some equations equal to each other, solve for the velocity, do a little bit of algebra, and some equations for the initial velocity so that things will be balanced out. All right, so the reason that I did this is we could add in potentially other objects and everything should kind of work out. So I could add another, well, first of all, let's see what happens if we change this to a 0. I believe Let's just see what happens. So we lost the sun. The reason for that is the sun basically is the center of mass, so you'd have the sun attracting itself. That's just an artifact of the way I'm calculating things right now, so the quick thing was just to skip it. So, alright, we just skipped that for now. Okay, so if I wanted to add something else, then I could add something completely made up. What if we add another Earth, maybe on the opposite side? Sorry, that's another Mars. Sure, we'll go with another Mars. We'll call it W for Wario or something like that. Okay, I can just add that in. I should see those M and W, so they're on the far part of my screen. I won't see them until they come around. So there's the M and there's the W. Alright, and it all just kind of works out because I can put a new object in. This set initial V based on the distance and the mass, it'll get it going at the right speed. Alright, so that is set initial V. Up to this point, we have the objects set up, they have their initial velocities, everything's great. But how do we know what's going to get drawn on the screen? Because these are huge numbers, right? This distance here, these are millions, right? This is 227 million. Right? If we're trying to figure out how many characters away or something, that's a much smaller number. So this set scale is going to set that up. Here's the set scale. So we have a variable max, starts at 0. We're going to go through each of the items. We're looking at each of the positions. There's something called dot distance. That dot distance is here, so this is there's two different versions here. So this returns the distance from the point to 0, 0. And this one returns distance from point to another point. So we have this one here is just the equation for distance. You have the square root of x squared plus y squared. And then we are down here in the set scale. So if the distance to a point is bigger than the max, we update the max. So this max is going to be the maximum distance from 0, 0. Alright, and the scale that we have is we want that to take up 40 characters. 40 characters because if we have 80 characters wide, then 40 characters would be the furthest thing we would see. We could change this to be, something else to make it fit on a smaller number of characters. Okay, remember, this is a pretty dense video. You might want to pause and explain things to yourself again. But that was the end of the load solar system, which came from here. This would be a good place to pause because everything's set up, and then we just need to look at what happens inside the loop. Let's see how we're doing on time. Pretty bad. We're going to keep going. All right. Now, there's three things that happen inside the loop. One of them is drawing with curses. That's probably the least math, so we'll look at that one. All right, draw curses. So this is a curses function. Clear the screen. So we start fresh every time we draw the screen. Down here, this is a curses function. Put new stuff on screen, not stuff. This tells it to redraw. So these, we're gonna have curses functions inside of here. So mv print w, print at position row column on the screen. So a certain number of rows down, certain number of columns across. So this puts a character there. It's like printf. So all that sort of gets stored in memory, and then this refresh says to actually do it. All right, then inside of here we have for each object, so 0 up to the size. This formula here is the row where it should go. So we have its position, divide by the scale that we had computed. That would be something that could be 0, let's see, row is 0 on up, could be negative, but the mv print w for mv print w, row is 0 at top, and larger going down, so row 0, 1, 2, 3, 4, and so on. And column is 0 at left, larger going right. That's just what the mv print w does. So this row here, instead of being something that goes 0, positive, 0, negative, this here makes it so that if we have something that is very positive for the y, what will happen to this? Something very positive, we have 12 minus, that will go smaller, which matches up with having smaller at the top. And something that's very negative here, there's a negative, so it gets larger, and that would go with larger going down. And the same kind of thing with the column. The column actually, we just do a scaling with where 0 is. You can think about that. All right, so that's it for the draw curses. If we wanted anything else to happen, every time we draw the screen, this is the place that we would put it. Say if we wanted to put a legend somewhere, if we want to put colors on these, that's probably going to go into the draw curses function. All right, we have two other things here, the update and the compute G. Let's look at the update because that's pretty easy. So for every object, we are going to change the position. So position has an X part and a Y part, and we can deal with them separately. So for the X part, we have a certain velocity that we have going in the X direction, and we do that for some amount of time, whatever the time step is. So for a little bit of time, we go ahead and move that position in this direction. Do it for X, the X part and the Y part separately. So that updates the position, and then we do the same thing for the velocity. Acceleration, which is all we have for acceleration here, is gravity. So gravity is going to change the velocity a little bit each time step. For a little bit of the time step, this velocity gets pulled in this direction. We do the X and the Y separately. This is also something that you're probably not going to have to change. All right, and then the only other thing left is the gravity calculations, which I believe we looked at in class for those that are taking the class. There's the compute G, and so for each object, what we do is we're going to recompute the acceleration. So for object I, I'm going to go over all the other objects and do gravity formula. So I do the gravity formula for updating the acceleration for object I based on object J. So this is something you're not going to have to change. Maybe we'll do a video with writing out the equations and seeing how they match up here. Okay, so I think that is a good place to stop video 1 of the planets. And the next video we'll maybe make a few little changes so that you still have this one. We'll do, let's see, planets, maybe we'll do version 1, and we'll copy everything out into version 1 and leave that unchanged. Okay, and right, so that'll be there, and that is the, so I'm not going to change that code, even to make bug fixes if there are any. All right, and then the next video we'll move on and make a few changes here. All right, have fun.